Hello, how is everyone doing? I hope you are learning and taking in a lot of knowledge from this conference and really getting in the mood of chaos engineering. Right up next, we have Liz Fong Jones. Liz is a developer advocate, labor and ethics organizer, and a site reliability engineer with 16 plus years of experience. She is an advocate at Honeycomb.io for the SRE and Observability communities and previously was an SRE working on products ranging from the Google Cloud Load Balancer to Google Flights. Today, she'll be talking about the socio-technical considerations after a blown SLO, and I'm sure we are all excited to hear what she has to say. So, the stage is all yours.
Thank you very much. All right, so let me just go ahead and get my slides pulled up, and then we can get started. So today we're going to be talking about what happens when you blow your SLO. Like what happens if you have a set of goals and you are not achieving them? How should you respond? Should you panic? Should you freeze all deploys, or should you do something else? So we'll talk about what your options are. So as was mentioned, I'm Liz, and I've been a site reliability engineer for a pretty long time. And I am really excited to share with you some of the lessons I've learned across companies ranging from, tiny startup like Honeycomb with, 20 engineers when I joined, to a large company like Google. But first, we're going to need to talk about what a service level objective is, just to make sure everyone's on the same page and level set. Then we'll talk about how you can ship to an SLO under normal circumstances, because it always helps to meet your SLO if you have a plan to meet your SLO. And then we'll talk about what happens when things go wrong and go boom. So what's an SLI? What's an SLO? Well, a SLO is described in Chapter 4 of the Google SRE book. And the idea is that you should not plan for 100% uptime, that you should have some idea about the level of reliability that actually is meaningful to your meaningful to your users, and you should aim to achieve just that level of reliability and not much more, so you're not spending money chasing nines that don't matter. The other cool thing about an SLO is that an SLO can help you avoid reducing your paging load, because if your customers are not in pain, maybe it's not worth paging for. So you can set your alerts only if you're in danger of violating your SLO, rather than on every single small sign of trouble within your system. The other cool thing is that with an SLO, you can actually use any leftover error budget, or the inverse of your SLO, right? The amount of allowed and availability. You can use that to perform chaos engineering experiments, as I'm sure you've heard during the rest of the conference. So let's talk about what Honeycomb's SLOs are, because this talk is about our own experiences as engineers at Honeycomb. So Honeycomb is a tool that aims to ingest telemetry from our customers to help them run more reliable systems. And then we allow people to search and query on every single column of that data, and regardless of how much cardinality there is, regardless of how many columns there are. So when we think about our SLOs and our objectives for success, we have some key flows that we want to make sure succeed, that are all mapped to real user journeys that our real users try to achieve. For instance, when you load the Honeycomb homepage, that should load relatively quickly, within 250 milliseconds. If you're trying to run a query as a user, that should take less than 10 seconds, but it can be a little bit more sporadic. It's okay for you to have to click refresh or reload in case it doesn't work the first time. But most importantly and pertinently to us, we only get one chance to ingest your data most of the time. There are some kind of proxies that will retry, but in general, we don't want to drop your customer data, because if we drop your customer data, especially for enough customers, those customers will wind up with a giant crater in their data for the end of time, which is not wonderful. So we aim to have 99.99% of the time that you get your events that you send to Honeycomb ingested without error in less than 5 milliseconds per event in the batch over a trailing period of 30 days. And that's less than 4.5 minutes of allowed downtime per month. That's not very much wiggle room. But the good news is that failures are not 100%, right? Like often we've designed our systems to make sure that they degrade partially. So in reality, if we have a 1% outage, we've got 400 minutes to fix it before we burn through the entire error budget. But we still kind of keep track of this idea of how much error budget do we have left, and what are we achieving versus what our goal is. So how do we actually do this, right? Like, as I said, 4 minutes of downtime per month, that's a really, really tight error margin. Well, here's how we actually do this. We start off by kind of adding instrumentation to your code and making sure that we have the appropriate functional tests. But most importantly, we design for feature flag development. That means that when we roll something out, we have the potential to roll it out gradually across our users rather than big bang rolling it out to 100% of our users or 0% of our users. And that minimizes the risks of things going wrong in 100% of production, as well as letting us do kind of these tests along the way to make sure that we understand, are things behaving the way that we expect them to or not? The other thing that we do is that we have really great continuous integration tests, and that those integration tests give us a high degree of confidence that our changes are at least going to superficially work in production. And that, in combination with human review and fast deployment cycles, means that we have the ability to quickly validate things before they roll out. We also don't have a large lead time between when we write a change and when we deploy it, which maximizes the amount of context that is in the head of the person who wrote the change right before it rolls out. So when they press merge, it actually just automatically reaches production within an hour after gradually progressing through a series of environments that introduce increased rigor over time. First of all, starting with our own environments. So we have a dog food environment that we use ourselves every day to observe production. And that environment gets all the changes first so that we can make sure that we eat our own dog food, so that we can make sure that we're testing the newest changes ourselves right before it goes to all of our customers. But here's the challenge. Not every experiment is going to succeed. There are always going to be some experiments that fail catastrophically. And therefore, it's important to know, what do you do if you either break your SLO or are in danger of breaking your SLO? So today, I'm going to spend the meat of my presentation talking about 3 case studies of failure and what we learned from each. We're going to be talking about when we had a failure of our Injust service, when we had a failure of the Kafka service that buffers all of our telemetry, as well as what happened when we did an experiment and degraded the performance of the queries of a majority of Honeycomb users, and how we stayed calm and kept shipping. So let's start first by talking about that Injust service, the one with the 4 nines SLO. So Shepherd is our stateless workers that are ingesting open telemetry format gRPCs, as well as ingesting JSON. It's a very, very high traffic environment where we very much care about throughput and getting the data ingested correctly. But at the time, we were only ingesting JSON. We were not ingesting gRPC. This was December of 2020. We needed to ingest gRPC in order to provide a more seamless experience to users who are using the vendor-neutral gRPC framework to send us their telemetry data rather than using our custom JSON API. So we were working on implementing this, and one of the changes that we deployed that worked fine in our staging environment on our local developers' workstations was that we were binding a privileged port by default. And we hadn't necessarily made sure that everything was working correctly on startup. So it tried to bind to a privileged port, it crashed on startup, and then it wouldn't serve queries. So we did have the right automation at this point to stop doing a deploy that was failing. But because we weren't yet using Kubernetes, there is no rollback of this. So any hosts that stayed broken were going to remain broken. And also, it was still the default new build that any new hosts were going to go and try to pull down the new version that was broken. So we were unable to scale up quickly enough because every single worker that Amazon stood up would simultaneously try to pull the new binaries, which was fine, and then it would start the binaries, which would crash, and then it would show 0% CPU usage, but it gets better. It would show 0% CPU usage, which would confuse Amazon and think that it had scaled up too far because now CPU utilization was too low, so it would scale in some other workers, even some of the busy workers. So then we would get this cycle where there's traffic coming off of our workers that were working correctly and going on to new workers that were broken. So we're in this yo-yo cycle in which latency was just going up and up and up as our users were unable to get their data. And therefore, we wound up impacting all of our users at once. So the Google SRE book might suggest to you, you should freeze your deploys if you blow your SLO. But we don't think that that's a good idea, right? We think that your deploy pipeline, your deploy machinery should keep working under all circumstances. Instead, what needs to change is you need to shift where you are spending your time as an engineering team, so you don't just pile up a bunch of changes that haven't shipped, but instead you're focused on using your existing running deploy pipeline to deploy improvements to reliability. So we definitely decided, we're not going to freeze deploys. There are plenty of other things that do need to go out. And also we think that it would be unnecessarily punitive to try to freeze all the deploys. Now, we did consider seriously the idea of delaying the launch. This was something where, we could say, you know what, we're not shipping this in January, it's fine. But this was a partner launch in coordination with Amazon Web Services because we wanted to advertise Honeycomb support of their new open telemetry distribution. So there were going to be some costs to delaying the launch if we didn't take some other action. So instead, we choose to get creative. We chose to spend some of our engineering cycles reducing risk. So previously, we'd been trying to kind of maintain deploying against a moving target to kind of add gRPC support along the way into our existing running Shepherd ingest workers. But instead, what we could have done and what we did instead was we chose to deploy a separate set of isolated workers that would be used only for gRPC. And we deployed a split to send traffic to gRPC at the Amazon load balancer to our special pool of workers, while continuing to keep the 99.99% of customers who are sending data with our JSON API happy and running on the previous setup. Yes, there was some risk that the Amazon load balancer change deployment could fail, but it's a relatively well-paved path to add a new listener rule, and is much easier to revert than accidentally taking out your entire cluster, which then has to be stood up again from scratch. So that's kind of how we met the deadlines of the launch, is we chose to keep on shipping, but to ship to a dedicated feature branch and frequently synchronizing those branches together so we didn't drift too far. And then after the holidays, we were able to finally get everything landed once it was stable and land it back inside of the main branch. All right, let's talk about the second time that we blew our SLO and what happened. So Kafka is our mechanism for providing a set of decoupling between the Shepherd ingest workers and our query workers. So it provides safety, but it also provides complexity. It introduces new dependencies and things that can go wrong. In particular, if Kafka breaks, then we cannot ingest data, no matter whether Shepherd is healthy or not. So in February of 2021, we are in the process of deploying Kafka on a new architecture with a new set of technology from Confluent, our Kafka vendor. And we're also moving from local disks onto Elastic Block Store. So this was changing 3 different variables at the same time. And we thought we had tested this in our dog food environment, which was about 1/3 the scale of production and something that we use every day. And fortunately for us, our dog food environment was not a true replica of the set of stresses that a production workload would represent. And therefore, what happened when we tried to roll this out and scale it out, having smoke tested it for over 2 months in dog food, was that we introduced chaos in production. We knew that there was going to be some risk of failure as this happened, but we underestimated how bad it was going to be. So we wound up running into 3 different dimensions that we had that we did not anticipate, right? Like we knew that there might be some scaling problems, but we kept on encountering issue after issue after issue. First of all, we blew out the amount of available disk bandwidth available to EBS. And it wasn't that we were blowing out the EBS dimension. We were blowing out the allowed amount of traffic to EBS from each individual AWS instance. And then after that, we blew out the network dimension of the amount of network capacity in and out that each instance would allow. And we tried scaling up. We actually accidentally deployed the wrong instance type. So we deployed the correct instance type. And even then, it was still really, really tricky. Because what would happen was like we'd be running, and we'd be starting to replicate data in. And then the instance would crash in Amazon. It would show up as instance terminated. And we all swore up and down, none of us had terminated instances. So at the end of the day, we had to go back and default onto a safe configuration. Instead of deploying all at once to AWS Graviton 2, tiered storage, and AWS Nitro, we said we're just going to keep local SSD. We're going to keep on Intel, and the one change we're going to deploy is the tiered storage to move older data onto S3. It was not worth it to us to burn out our people chasing just a small amount of money at the time. And it took until December 2021 with the release of Graviton 2 instances with local storage, the IM4GN instance type, for us to finally feel that we were able to move forward safely with enough learnings from what we had done in January of that and February of that year. So what we learned from that is that even if you anticipate that there may be some chaos for making a change, you should always have a mechanism and a safety cord to pull to say, you know what, this is not going according to plan. We need to back out from the experiment and try something else. We need to take care of our people first, because even though we didn't blow our SLO in terms of the service, we had, through heroics, kept our SLO working correctly. The cost to our humans was not worth it. We had, for instance, a bunch of people that had worked really late hours or had interrupted families dinners with their family, and that was not okay. So as a result, we did a couple of changes, right? Like, first of all, we stopped the deployment. We failed safe. And we also said, you know what, like, if you had to go and, if you didn't have the energy or bandwidth to cook dinner for your family because you're working an instant, just expense dinner. It's on us, right? Like, you're expected to speak up at Honeycomb if you feel something's not safe or not working right. And that's definitely something that happened here. All right, let's go ahead and talk about the third and final failure mode here, which is we have a query service that makes extensive use of AWS Lambda. And one of the challenges that we were encountering was that we were having extreme cost associated with AWS Lambda, and that the performance was not quite what we wanted, that we were encountering limits with how wide we could scale up, as well as how much it was costing us, because Lambda charges by the millisecond. So we decided that we were going to leverage a new AWS announcement to allow use of Graviton 2 ARM64 processors on your Lambda functions. So I'd originally switched us to, hey, let's just do a straight A/B test, 50%, 50%. This is fine, right? It turns out doing so cold on a giant workload that is straining the capacity, not a good idea. So we went straight to 50% and it just blew up in our faces right away. Like, latency went up by a factor of 3. But the good news here is this was feature flaggable. We did not actually blow our SLO because we were able to quickly roll back and remediate the impact. Within seconds, literally seconds, like I flipped the feature flag at 6:48:15, and by 6:48:35, we dropped off the problematic traffic back down to 0, or close to 0. We dropped it back to 1%. So this kind of experiment is something that becomes normal and routine if you have feature flags, because it really enables you to do this process of iterating on something, knowing that you have an out in case it goes wrong, and knowing that you have an upper bound on the number of users that you can impact. And then after that, we started carefully making progress, scaling up from 1% to 20% to 30%. And we're sitting at 30% today while we wait and continue to gather feedback between us and the AWS team on how we can move forward safely. So my message to you is that fast and reliable do go together, that it's kind of like riding a bicycle. That if you ride a bicycle really, really slowly, like a kid who's just learning to ride their bicycle and is terrified to push the pedals, yeah, you're going to fall over. But like if you keep on moving and making forward progress and carrying on momentum, that means that you're going to be in a more stable state than if you kind of stop cold and then have to start over from scratch every single time. So you can design for reliability through your full life cycle, and especially using feature flags to help keep you within SLO. And even when you can't use feature flags, you can use other techniques such as segregating more experimental traffic, using your infrastructure, or especially discovering and spreading out risk to improve your customer experiences. And if a black swan happens, for instance, you just have to patch log4j yesterday, it's okay to do things that are a little bit more disruptive, because your SLO is, at the end of the day, just a number. Customer happiness and customer satisfaction is what matters. And customers will be understanding that they would rather tolerate a little bit of unreliability than to have all of their customer data leaked all over the internet. The other interesting lesson here is that you can discover hidden risks through doing testing. For instance, we've adopted this technique of using chaos engineering in order to restart one retriever worker and one Kafka broker in each environment every week, like clockwork, so we can verify that our instance replacement works and that we can hold up during the increased load, even at weekday peak times when we have to replace an instance, rather than discovering this when no one's at work and therefore struggling because all of our automation is broken. So we continuously validate our infrastructure, and that's how we have the confidence to know that we can meet our SLOs in the future. There are other things you might want to be aware about, like SSL certificates and DNS. Stuff does happen, so just have a plan to address it. And once you've made experimentation routine, and once you have systems that are sufficiently self-healing, it turns out that it's worthwhile to try experiments. For instance, you can non-jokingly suggest, hey, it might be okay to go ahead and just deploy the chaos monkey, right? Like, and set it loose and just like restart services at random. But you don't just, dive directly into that. You have to start by doing thoughtful experiments first and uncovering kind of all of your known source of risks and remediating it before you start introducing the potential for unknown sources of risk. So at the end of the day, we're all part of sociotechnical systems. We're all customers, engineers, stakeholders. And if you have an outage or a failed experiment, you shouldn't fire the person who did it, right? Like, it's an unscheduled learning opportunity. Make the most out of it. SLOs are ultimately the result of discussions between different people, different teams, and various stakeholders. So figure out what the optimal way is to optimize customer happiness rather than necessarily saying the SLO is the only thing. Put customers first and talk to each other, and you'll figure the rest out. Thank you very much. And if you're interested in learning more, I do have an upcoming book with O'Reilly coming out titled Observability Engineering. And you can go check it out at honeycomb.io or go check out other things about kind of our experience with operating large resilient systems at Honeycomb. So with that, I'm happy to take any questions that you have. And I see that a couple have come in, so I'll go and look at the Q&A tab. Kartik asks, do you stack SLOs by criticality? Oh, Sayan, are you going to read the questions to me?
Yeah, you can take it as well. That's fine.
Okay. Do you stack SLOs by criticality? Some are negotiable and some are tolerable. We do have tiers of SLOs by the percentage threshold. So, right, like, if a 99.9 SLO blows and a 99% SLO blows, we're going to treat the 99.9 one with more urgency because we have less time before it actually fully goes wrong. Whereas the 99% one, we can allow to go for, several hours before it becomes a serious problem. So that's kind of one answer. The other answer is that we think it's really important to be able to debug your SLOs and to understand what's the actual user journey, right? What are users trying to accomplish? So in terms of chaos testing, obviously you have to be more careful when you experiment with a tighter SLO. Cool. I think that answers that question. Do you want to give me another question?
Yeah, I guess we can take another one. So let me just share this on stage. So what was the particular metric that you showed in the diagram as a SLO blown?
Yes. So what I was showing was this set of diagrams, right? So over here, what you can see is that we have a budget burn down. How much of our error budget have we spent over the past 30 days or 90 days or whatever your SLO is? And, how much is left and where did we spend that budget? How have we trended for each ruling window over the past 30 days, looking back 30 days? And this diagram here, I think, is super interesting, right? Like, this highlights a heat map of response latencies and time that is elapsed and how many requests is the saturation. And any yellow flagged ones are errors, things that either were too slow or that generated errors. So you can see, right, like that if this starts degrading really, really quickly, what you'll see is you'll see a big lump of yellow. And what I didn't show here, because that's kind of more Honeycomb specific product stuff, and I don't want to get too vendory, is right, like you do have the ability, at least in Honeycomb's SLO tool, to see what are the common factors, right? Like what are the correlations between your failed SLO and what fields in your telemetry data. And that can help you root cause and figure out, like, what do I need to do to remediate this? What do I need to do to fix it? Or who's particularly badly impacted? Who should I reach out to? So that's kind of how we think about this problem of how do you visualize an SLO? But there are many different valid takes on this. For instance, Blameless, who are a sponsor of this and who I'm an advisor to, right? Like they also have a really great way to visualize SLOs. So there are a number of different ways to look at SLOs, but I think the most important thing is, can you see where your SLO is burning? Can you get a notification, ideally, predicting into the future, when are you going to blow your SLO? We do that too. And then, can you quickly debug it? Those are kind of some of the most important factors.
Awesome. Sounds great. So there's one more question by Suresh, which says, do you involve your change management if SLO is blown to restrict the release?
No, we don't currently automatically do kind of change management or blocking releases. And the reason for that is that we view it as important to keep on rolling out releases. If there's a blown SLO, that's a consideration for, we're going to have a talk about what the priorities of the team are for the next 6 weeks. That's not a, immediately halt the presses. Unless there's something that goes wrong. Like we did have an outage we spoke about publicly about a year or two ago where we deployed binaries where there was, you don't need to share my screen here. We deployed a release that contained no binaries, and we lacked safety mechanisms to roll it out safely. And there we weren't confident it wasn't going to happen again, where a compile bug could take out our entire cluster. So there we halted releases until we'd fixed the automation and until we at least remediated enough of the release process to ensure that we can move forward safely.
Awesome. So let's take one last question before we wrap this up. So another question is, do you handle resource issues differently, especially thinking of resources you maxed out at your provider?
Yes and no, right? Like if there's a resource issue, then you kind of have to, here, let me go forward back to the relevant slide. Right, like so when you have a resource issue like this, where, ostensibly it's serving the same number of requests, but they're all piling up and getting backlogged. You kind of just have to scale back, right? Like you have to find ways to shed load, right? If your provider cannot keep up, then you have to shed load or send it elsewhere, right? Like in this particular case, there wasn't enough ARM capacity available. That's fine, right? Like it was the first week after they launched, right? So we're like, okay, that's a failed experiment. We'll just roll back, right? Like we'll send the traffic elsewhere. So if you can't load shed, right, and all of your traffic is critical, then and your provider isn't providing you with resources or communication, you better find a new provider. But here we found AWS to be very responsive. They're happy to get back to us about our concern and help us work out a path forward.
Thanks.
All right. Well,
yeah, go ahead.
I think any further questions, we can go ahead and take over to the Slack.
Yeah. So thank you for the detailed answer to all the questions. It was a really amazing session and very insightful for advanced beginners, intermediates, everyone. And yeah, so if you have any more questions, head over to slack.chaosnative.com. There's a channel called Chaos Carnival 2022. So go over there. I have already created a thread and tagged Liz as well. So feel free to ask your questions on that thread and she'll be happy to help you out. Awesome. Now we have two more sessions coming up, which is one is reducing error budget depletion with chaos engineering, and another is talking about how team resilience score can be calculated. So they are really interesting sessions. So feel free to join them post this one. And thank you again for joining and having such an insightful session. Thank you, Liz.